Hi, thanks for joining me. Today I've got a fun infinite series problem. We have k, a natural number, and we want to calculate this thing here, the infinite sum from n equals 1 to infinity of 1 over n squared plus kn. Okay, so if you want to have a go at evaluating this sum here, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so the way we're going to do this is a bit of exploration. So I've just called the sum here that we're trying to work out, sk, and well, let's look at some small cases. So when k equals 1, k equals 2, and then perhaps we can spot a pattern. Okay, so let's look at s1, so when k is 1. S1 is just precisely the sum from n equals 1 to infinity of 1 over n squared plus n. But of course, n squared plus n is just n times, in brackets, n plus 1. So I can write this thing here as a sum from n equals 1 to infinity of 1 over n plus 1. But then I can split this guy here by partial fractions. So this thing here is the sum from n equals 1 to infinity of 1 over n minus 1 over n plus 1. Okay, and just to check that this thing equals that thing, we can just sort of cross multiply. So we get n plus 1 there minus n. So at the top we just left with 1. And on the bottom we have n times n plus 1. So it's exactly that thing there. But now this is just a telescoping series. If we plug in the first few terms, so the first one when n is 1, we get 1 over 1 minus 1 over 2, then plus 1 over 2 minus 1 over 3. So this is the case n equals 2, plus, now in the case n equals 3, 1 over 3 minus 1 over 4, plus, and so on. The minus half here cancels with the half here. The minus third there cancels with the third there. The minus quarter will cancel with the quarter, and so on. So all we're left with is this starting term here, 1 over 1. Okay, so we have the S1 is just 1. Okay, now what we want to do is explore S2 and S3, and then see if we can spot a pattern. Okay, so now let's look at S2. So S2 is a sum from n equals 1 to infinity of 1 over n squared plus 2n. And again, what we want to do is factorise this and then split it into partial fractions. So I'm just going to jump into splitting it into partial fractions. This thing here is the sum from n equals 1 to infinity of a half 1 over n minus 1 over n plus 2. Okay, and just to see this, when I cross multiply, I get n plus 2 minus n on the top. So that's just 2 on the top. And on the bottom I get n times n plus 2, so I've got 2 over n squared plus 2n, but of course here we've got 1, so that's why we've got this factor of a half. But of course I can just bring this factor of a half to the front. So this equals this guy here, and again with this sum here I can just use telescoping. Okay, so let's write out the first few terms again. So this is a half, well, let me write this in square brackets. Okay, the first term when n equals 1 we get 1 minus a third. The second term is a half minus a quarter. The third term is a third minus a fifth. The next term is a quarter minus a sixth. Ooh. And so on. Okay, so now it's the third here cancels with the third here. The quarter here cancels with the quarter there. The fifth here will cancel with the fifth here. The sixth here will cancel with the sixth there, and so on. So all we're left with is the 1 over 1 term plus the 1 over 2 term. So that's 3 over 2, or 1 plus a half. Okay, and then we've got this half term out front. So S2 is just a half times 1 plus a half. And you'll see why I'm writing it in this way in just a second when we look at S3. Okay, so now let's look at S3. S3 is a sum from n equals 1 to infinity of 1 over n squared plus 3n. Again, we're going to factorise this, use partial fractions, and then use telescoping. Okay, so in partial fractions form, this is the sum from n equals 1 to infinity of a third times 1 over n minus 1 over n plus 3. Okay, in the end, you can just quickly check that this equals this by cross multiplying, so we'll have 3 on the top and then n squared plus 3n on the bottom, but of course the 3 cancels with a third at the front there. Okay, so I can bring the third out to the front of this sum, like so. Okay, and now we've got something that's nice and telescoping. So this is just a third. Let's plug in n equals 1, so we get 1 over 1 minus 1 over 4. When n equals 2, I get a half minus a fifth. When n equals 3, I get a third minus a sixth. And hopefully you can just see what's happening now. When I put n is 4, I get a quarter minus the 7th, and I'll do one more term, 1 over 5 minus 1 over 8. Okay, the minus quarter here cancels with the plus quarter there, the minus 5th here cancels with the plus 5th there, the minus 6th here will cancel with the plus 6th in the next term, and so on. So all we're left with is 1 over 1 plus 1 over 2 plus 1 over 3, and of course we've got the third out front, so we get the S3, let me write it here, S3 is equal to a third, 1 plus a half plus a third. Now hopefully you can see the pattern. We have S1 equals 1, S2 equals a half times 1 plus a half, S3 is equal to 1 over 3 times 1 plus a half plus a third. So now let's make a conclusion about SK. Okay, so it's not too difficult to make a conclusion about SK. You can sort of repeat the argument with generic K. So we have S1 equals 1, S2 equals a half times 1 plus a half, S3 equals a third times 1 plus a half plus a third. And you can conclude that SK, you can just look at the proof again and modify it for K. SK is equal to 1 over K times 1 plus a half plus a dot 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 plus 1 over K. And this thing here is precisely the kth harmonic number, which is denoted HK. So HK is simply this sum here. And of course we've got the 1 over K out front. So SK is precisely HK over K, which I think is quite nice. It's combining the harmonic sort of series and just the reciprocals, which also is involved within the harmonic series. Now you might ask yourself, what is the limit as K tends to infinity of SK? Well, we can just use this thing here. We know that the harmonic numbers grow logarithmically, so they've got sort of something that's like log K on the top divided by K, and of course because K grows a lot faster than log K, this thing will tend to 0. So SK tends to 0 as K goes to infinity. Anyway, that's all for today's video. I hope you have enjoyed it. If you're new here, please do consider subscribing and checking out some of my other fun maths videos as well. But that's all for today. I will catch you in the next one. Have a great day.